Okay, let's start. Welcome back, folks. Well, we're finishing off week 12, so this marks the 75% portion of the entire semester. And we got through the third exam, so congratulations is in order. This is a pretty tough exam, I'd say, because section 4.1 just feels like a severe jump in abstraction compared to the other work we've done and the other topics on that exam. There was a few questions from 4.1 directly on this exam, but I'm going to grade them with the understanding that this section is a bit of an outlier. So if you did some good work on that, there's going to be lots of partial credit awarded. I intend to have the grading done for exam 3 sometime Friday morning, but there's sometimes a delay. I had a delayed last round of exams where some of the testing centers are sending them out kind of like 5 p.m., 6 p.m. on Friday. So if something like that happens again, I'll have grading completed on Saturday morning at the latest. And if you are taking the class fully online, just like last time, I'll be emailing you back your exam, your current course grade, which will be the same course grade you see here on the Canvas web page. If you're the in-person class and you just like your exam back sooner, don't hesitate to email me again. Anything you say, just I'd like to get my exam back. Just a short message will be great. And I have no trouble getting a scan in to get your exam in sooner. Well, that's what we're dealing with so far in this week. We got through the big stressful portion. And now we're just about done with chapter 4. This is going to be our last section before we close it out and go into chapter 5. And chapter 5, chapter 6, the main idea there is now we're looking into applications of everything we've learned about vector spaces, linear transformations, and our other methods. Chapter 5 is going to be about the eigenvalues, eigenvectors. We'll particularly be looking at just the mechanics. It'll be a short tour, 3 sections, but that's where there's tons of mathematical applications to physics, engineering, all sorts of other things, economies, differential equations, and so on. Then chapter 6 is another application section. That one's more about the geometry of a vector space itself. We'll look at angles between vectors, other interesting facts about orthogonality as well. But I think I'm out of announcements at the moment. Any last questions at all, folks, before we get started? Okay, well, section 4.5 is exciting because we've very loosely talked about dimensions of vector spaces. We've said things along the lines of R3 is a 3-dimensional vector space, but we've never really had the opportunity to fully say what we mean by dimension exactly. In order to do that, we had to know what a basis was. So that's the role of section 4.3. And just as one more quick overview of how all the definitions stack up, here's what we're looking at in section 1.3. We had to define what we meant by a linear combination. In some sense, this is one of the most fundamental ideas because through the linear combination, we define the span of a set. We also defined linear independence, having only a trivial solution to a homogeneous system. And those two elements gave us what we meant by a basis. Finally, if you have a basis, section 4.5 does the important task of giving us 2 more crucial theorems, 2 more important facts about bases we need to know about vector spaces to finally give a definition of dimension that's well defined. So that's where we're at so far. Because this depends so much on what a basis is, let's take a look at that just as a quick review. So a basis for a subspace of a vector space V is just a collection of vectors, B1, B2 through BP, and those vectors have to be linearly independent and they have to span the subspace H. So that's the only requirements. And a lot of problems we do, H is a proper subspace. It's a proper subset of the vector space V. In other problems, we just use this whole definition on the vector space V itself. So that's our refresher on basis. And now this gets section 4.5 started. Here's the first really important theorem, theorem number 9. It says if a vector space V has a basis, B1 through Bn, containing exactly n vectors, then we have one immediate and very important fact. Any set in V containing more than those n vectors is automatically linearly dependent. So this is the first big fact we need about a basis in order to define what we mean by dimension in the first place. And just for a really fast example, let's suppose we have a set that goes, let's let it be b equals 1, 5, comma, negative 2, 0, comma, 6, 7. This is a subset of R2. My claim is that it's linearly dependent, and you probably already knew that based off problems we've done so far. But using this as a simple example, tying it together with theorem number 9, here's the other related fact that we can discuss. R2, where all these three vectors in B came from, has a basis. Let's write this out as, we could give it the standard ordered basis, E1, E2, or we can give it a slightly different basis, 1, 0, 1, 1. That definitely qualifies as a basis. But this basis has exactly two vectors. This has two vectors. So the moment we found a basis for the vector space that we're interested in, that's R2 in this problem, the moment we know that one basis has two vectors, any other listing of more than two vectors, that's in the set B, automatically tells us immediately at this stage, B is linearly dependent. So we can conclude, therefore, B is linearly dependent since it has three vectors, more than that basis over here of two vectors. So it's a cool little theorem. We didn't always have to use a theorem like this. When we were way back in section, I believe this was 1.7, we saw a listing of vectors v1, v2, v3, like these three here. We said that this set is automatically linearly dependent because of a different theorem. There's just more vectors than entries per vector in that set, and that guaranteed linear dependence. The trouble with this theorem 8 is, in chapter 1, is you can't use it for a set like this one in P2. This was really constrained in Rn specifically as a vector space. And so theorem number 9 is just the more general way to think about this. It could be any vector space V whatsoever. So that's our brand new theorem. We're going to need one more tool along these kind of lines in order to define dimension. And here's just another quick example, example 1, using theorem 9 itself. Any questions at the moment with the discussion about what theorem 9 is all about? Okay, well, let's work through example 1. We want to show why this set B right here is linearly dependent. And I wrote it with that fancy script B or cursive B, but using a fancy font doesn't automatically guarantee it's a basis. One thing we'll do to start this out is, in view of theorem 9, let's find just any basis for P2. We can say this, script E equals 1 t squared is the standard basis for P2. We use this basis quite a lot in the last section in particular with coordinate systems. It's the standard basis for P2 and has three vectors. So there's now more than one way to answer part B. You could use the isomorphism, the coordinate mapping, to transfer this problem from P2 into R3. Then you'll have a matrix that you can row reduce, you can analyze the pivots and show linearly dependent because there is more columns than entries per vector in those columns. Or you could just simply say, how many vectors are in the set? Let's go that route. We're using theorem 9 at this point. The set B has it's comma separated, so let's carefully count them. 1, 2, 3, 4 vectors in total. which is greater than the three vectors in the basis E. So our work is done. That's kind of an amazing theorem 9 in a certain sense. The moment we found more vectors than one particular basis, we can immediately conclude, therefore, B is linearly dependent. So this starts to give us now a really big hint. The dimension of a vector space feels like it's intrinsically tied to the number of vectors in a basis. R2, any basis you write down, looks like it has to have specifically two vectors, no matter what you try. But if you're working more foggy vector spaces like polynomial spaces, function spaces, we need that fact to be true as well. And so that is what makes the next theorem really a fantastic one. Any last questions, folks, before we get into the next theorem?
I was wondering about the notation. Just like, why do we have the hyphen between the number and vectors?
Let me take a look. Oh, right here.
Yeah.
I would say that was just a weird stylistic choice, the way I decided to write that. It would have been just fine to leave it without the hyphen in this kind of way. I'm not too sure why I wrote it that way, to be completely honest. Some reason I put in a hyphen, but that was just a
Yeah, I
weird
mean,
oddity for how I was writing.
it seems like the author did that too. So, yeah.
Probably where I picked it up, actually. Yeah, really more
Yeah.
just a stylistic flair in the writing. Thanks for spotting that, though. That is kind of an interesting point. Let's leave it on this one just to convey it's a fine way to say it. But let's leave
Yeah.
it off of this one to say you don't have to write in that form.
Okay, cool.
Well, thanks for mentioning that. I've never really thought about that, so I appreciate that question. Other questions at the moment? Okay, well, let's take a look into the next big theorem. Really short and sweet. But when you think about this, this is really saying a lot. There's lots of different bases you could give for, say, R2, for example, standard order basis or the funky basis that we put down. But theorem 10 says there's something intrinsic about vector space and the basis that you write down, any basis. Every basis, well, this part's critical. If a vector space has a basis of n vectors, so let's admit that we're saying one thing very specific about our vector space V. If it has a basis of n vectors, one thing we said is there's a finite basis. So theorem 10 only works if V has a finite basis. That deserves to really emphasize about this. So if you have a finite basis, then it turns out no matter how creative you decide to write down your bases, every single basis of that same vector space V will contain the same number of vectors, exactly n. So those portions are always going to match up. Thinking in terms of R2, that means anytime you write down a basis for R2, there must always be exactly two vectors. Similarly for R4, any basis for R4 must have exactly four vectors and so on. So that makes these problems kind of quick as well. We're explaining why this set of vectors from R4 cannot form a basis in R4. Well, if you write down the basis for R4, we're expecting exactly four vectors. This set has three vectors, and then by theorem 10, our work is done. We are expecting four to have even a chance of getting a basis. Well, let's write out all the details in full. A basis for R4, let's let it be the fancy one, the standard order basis. Standard ordered basis goes E1, there's a 1 there. Let me fix that notation. E1, E2, E3, E4, where EI is the ith column of the 4x4 identity matrix. For example, we wrote down E3 in full, this one would be 0, 0, 1, 0. Prior times when we wrote these down, we said exactly what each one of them are, but we've encountered these vectors so much. It's okay if on your paper you were just to leave it like this. Using E would imply you're talking about the columns of the identity matrix. The key fact about this is R4 must contain 4 vectors in any basis. So the vector space R4 is taking the role of the vector space V in the theorem 10 above. And now our work is just instantly done. The moment we know what the basis looks like, whether we wrote it down on paper or not, the moment we know how many vectors it has, 4, the set B here is automatically not a basis. We can say here, just to finalize it, it's just pretty much a conclusion at this point. By theorem 10, that's supposed to be a B. B is not a basis for R4 because it only has three vectors. And I did that hyphenated thing again. Well, we did it, folks. These are some pretty fast problems that give you great alternatives to determining if something is a basis or not. Too many vectors, and you cannot be a basis if you have more vectors than any basis, and too few vectors, and you cannot be a basis at all. So theorem 10 is now telling us that number n is actually really special. Any vector space you put down, if you spot a basis, if it has a basis of n vectors, so it's finite dimensional, that number n is what we mean by dimension finally. N is the number of vectors in a basis defining dimension. Theorems 9 and 10 tell us this is well defined. You cannot put down a vector space which has a basis with a different number of vectors, is what those last two theorems are telling us. Now, if we put this all together, we're ready for the formal definition of the dimension of a vector space. Any last thoughts so far getting through this one? Okay, really with where we're at so far in the linear algebra course, really we're just putting down some finishing touches to a huge collection of facts that we've gone through. Defining dimension is not too bad at this point because we've done all the hard work at this level of linear algebra. Spanning linear independence, dealing with bases and all that, tells us finally, here's the short and sweet definition for a dimension. We'll say if V is spanned by a finite set, then V is said to be a finite dimensional vector space, and we define the dimension of V written as simply dim V, as if we're using function notation, which is appropriate. That's an honest function. Dimension V is the number of vectors and a basis for V. So that's a nice definition. Prior theorems tell us that this is now a well-defined function because every basis has the exact same number of vectors. So just for a few examples of what this could look like, let's write down a couple problems. That's what these blank examples are all about. There's finite dimensional and also infinite dimensional as part of the definitions. So for something that's finite dimensional of dimension greater than 0, we could say let H be equal to span of 1, 1, 5, 0, just a random set of vectors in R4, negative 1, 0, 0, 1. At this point, we can determine the dimension of the subspace H of R4. Why is that? We have a spanning set. That's half the dimension of what we need for a basis. Let's pull this up just as a quick reminder. We have spanning is already taken care of for that set H. And also because this is specifically two vectors, we can determine linear independence by inspection. The first vector is not a multiple of the other one. And we can see it just from the 1 going into a 0 here. So this is also linearly independent as a set if you take off the span word. So we have a spanning set that's linearly independent. That means a basis is ready to go here. A basis for H is, let's call this V1, V2 for brevity, V1, V2. And at this point, we can make the big conclusion. The dimension of the set H is 2 because that's the number of vectors in this one basis. And no matter what you change the basis into, it'll always have specifically 2 vectors inside of it by the prior theorems. So again, it's kind of a nice definition. Just count the vectors in a basis and you have the dimension. Well, dimension is an integer that's non-negative. Dimension could also be 0. This is where the trivial subspace, the set of vectors that contains only the 0 vector, this is a vector space in its own right. This one is the only type of vector space that has dimension 0. And this comes up a little bit more often than we might think. For example, if you say, let A equal 1503, then we can say some interesting facts about A. In fact, it's invertible. Let's write out the determinant. Determinant A is going to be 3 minus 0, which is not 0, which implies A inverse exists. What that will then tell us is the null space of A. This is the set of all solutions to the homogeneous equation AX equals 0. Let's just write that out just for a reminder. The null space of A is a set of all vectors X solving the homogeneous equation A times X equals the 0 vector. But if A inverse exists, then A times X equals a 0 vector has only the trivial solution. So this set contains just the 0 vector. That means if we were ever asked what is the dimension of the null space of the matrix A, that dimension would be 0 because the null space is just the trivial vector space containing only the 0 vector. So that's one way the 0 vector comes out, the way we'll often see it the most, usually in the context of the null space coming up. So these are the 2 usual situations, a positive dimension, a 0 dimension. And this is the weird stuff when it comes out to be infinite dimensional. We'll explore some of these topics if we have space at the very end of class today. But any questions at the moment with these first 2 quick examples? Okay, well, we have a couple good examples of what could be infinite dimensional. One is the set of all polynomials at any degree whatsoever. If you write out this, P, and you don't say P3, P4, P5, you mean any polynomial whatsoever to any degree. This is the vector space of all polynomials. Because there's infinitely many polynomials here, we can't use a trick like writing out E equals 1t squared t cubed to write down a basis that's finite. This basis is infinite. If we have it finite dimensional, that means it's spanned by a finite set V. This one's not. You have to keep going here for all orders, or not T1, T2, T3, but rather t squared, t cubed, and so on. You have to put in all degrees of these power functions to start to form a basis for P. So it's not spanned by a finite set whatsoever. You might as well just throw that right on here just to put those thoughts together. Because it's not spanned by a finite set, we say dimension of P, it's infinite dimensional, and the shorthand way of writing it is just saying dim P equals infinity. And this is again because P is spanned by an infinite set. One, t, t squared, t cubed, and so on. So that's definitely not a finite basis. Another one that came up is this vector space C on the closed set AB. This one's the set of all continuous functions f on the domain A to B. There's a lot you can say to this. We gave it a name in the prior notes that it's a complete Banach space. So the major thing about this one is the dimension of CAB is also infinity. So these are two pretty weird vector spaces. It feels like P should have been a simpler one, but it's in fact, in terms of dimension, just as complicated as CAB. Well, any last questions, folks, with the rundown of the definitions, finite versus infinite dimensional? Okay, for the next part of the notes, we're going to crank out some dimensions. Really what's going to happen in example 3 and in example 4 is these are kind of decent review problems of section 4.3 itself. First thing we're actually doing on them is finding a basis. That's our part A. Then we'll connect the new concept and say, based on the basis we found, what's the dimension? So again, pretty much a review problem on both of them. Section 4.3 is tricky, so this is well worth our time. To find a basis for this space, notice it's essentially a column space. You can break down that vector by the red dot into parametric vector form. You can rewrite it as a spanning set, throw it into a matrix, and then just look for the pivot columns. So that's the approach that we took. Let's see here. I believe in section 4.3 on this problem, if you have a span of a set of vectors, theorem 6, which was really just the quick way to view the spanning set theorem, tells us the pivot column of that matrix A formed by these vectors, those pivot columns form a basis. So if we can get the spanning set out of this problem, it's just a redo of that second to last problem in section 4.3. So let's just start by writing out H equals. The parameters are A, B, and C. So go A times coefficients, 3, 0, -7, -3. So those are all the coefficients of A. Then go plus B. Take coefficients of the parameter B. We'll start off with a 0, -1, 6, 0. Then coefficients for parameter C go 6, -1, -8, -6. Then we can say such that A, B, C are in R. But then this becomes a definition on spanning. Spanning of a set of vectors is exactly the structure that we see. So if we'd like, we could rewrite it as span 3, 0, -7, -3, 0, -1, 6, 0. And last, 6, -1, -8, -6. Okay, barely got that bracket in. So now that we have 3 vectors, the next thing that's kind of dangerous about this problem is we can't celebrate too early on this. It's not guaranteed to be a basis. This is just half the information we need for a basis, the fact that it's a spanning set. We also have to determine if the columns are linearly independent, and that's not a guarantee. All I can tell you for sure is that the dimension of H is at most 3, but it might be of a smaller dimension. Well, let's take another look into this. If we take and let A, let's give these names, V1, V2, V3, we let A equal V1, V2, V3, then we can investigate the pivot columns of A, and those pivot columns will correspond to the vectors here, which are linearly independent. So A is now equal to 3, 0, -7, -3, 0, -1, 6, 0, 6, -1, -8, -6. Feels like we wrote down those vectors quite a few times. And now to do the row operations, we can immediately add row 1 to row 4. Let me take one extra step because row 3 is a little bit nastier with the 7 there. I'm going to just divide row 1 by 3 to start this off. So now we have row equivalents, 1, 0, 2, 0, -1, -1, -7, 6, -8, -3, 0, -6 going row-wise. And now we can start wiping things out below that first pivot here. So 1, 0, 2, we can copy in row 2, just as is, 0, -1, -1. 7 times row 1 added to row 3, it's going to give us 0, 6, then 14 minus 8 for another 6. Triple row 1 added to row 4 gives us 0, 0, then 6 minus 6 for 0. And then automatically, row 3 is zeroed out. You can take 6 times row 2 added to row 3 to wipe out those both entries. And so now it's row equivalent to 1, 0, 2, 0, -1, -1, and then the 2 zeroed out rows. That makes this problem kind of surprising. I don't really see a dependence relation just by eyeballing it here. But after doing the row reduction, only columns 1 and 2 are pivot columns, is what I mean to say. That means V3 is in fact a linear combination of V1 and V2. Spanning set theorem, or theorem 6 and 4.3 says we can just literally delete it and conclude a basis for H is these two vectors. We don't put span any longer. We're not trying to write out the set H. If we want to write out what H is, we would span these two vectors. But if we're writing down a basis, it's just those two vectors specifically. So 3, 0, -7, -3, 0, -1, 6, 0. Another concept to think about on why we dropped the word span here is there was also a homework question, I believe in section 4.3, which says, if you span a set like this, and it has something other than the 0 vector, this collection has infinitely many vectors in total. This is not infinite dimensional vector space, H. It's finite dimensional. And so that's when we state the basis, we take off span. It's just those two constant vectors we're concerned with. Now part B is effectively done right at this stage. This is kind of nice. We can say, therefore, dimension of H is 2 because there's only two vectors in the basis. So all the hard work is actually getting the basis itself. Saying what the dimension is the fast problem in these notes. What we did, folks, that's kind of a review problem. It's very similar to what we did in section 4.3, with just more added terminology. Any questions at all getting through this one? Okay, maybe one more thought about dimension. Let me put a little box here to say this is an additional remark, not part of the problem. What's kind of interesting about dim and using this very suggestive function notation is that dimension is in fact a function. Dimension is a function that goes from V. V is a vector space. There's something intrinsic about vector spaces. The number of vectors in a basis is always the same. So dim maps from V into Z non-negative. So this is the set of integers that are non-negative. Well, that's almost true, as long as V is finite dimensional. So it maps into the set union. If it's infinite dimensional, we also wrote infinity down. So it maps into this entire set, the non-negative integers, or into just this symbol, in the case we have an infinite dimensional vector space above. So just another interesting mapping that we're looking into once we've defined dimension. And that's why we call it well-defined. It's well-defined as a function. And here is the function form from domain into codomain. So let's take another look into a problem kind of like example 3. Example 3 is essentially just a column space. This equals column space of A, and the specific matrix A is this one that we listed right here when we threw in the 3 columns that are spanning. This one's different. This one is now a basis for a null space if we can get it into the right format. It's slightly annoying because the notation is going sideways. We have a system of equations, but we haven't put the variables all on one side. So it's just complicated to visualize. So a lot of the work we do on example 2 or example 4 is just cleaning this up. Let's see if we can turn it into a null space. So let's rewrite H. I'm going to switch out this vector here into a bona fide column vector, A, B, C, D. Occasionally, the author does write it this way to the homework problem. So putting it back in the notes is just a reminder. This is another important way to visualize this. For the system of equations, I'm going to clean it up and put all the variables to one side, the left-hand side. So this is A plus 2B minus 3D equals 0 on equation 1. On equation 2, let's maybe format this slightly more suggestively. Variables go A, B, C, D. So let's get a little gap before plus 3D equals 0 on equation 1, just for the sake of organizing. Equation 2, here's where C can go. C then minus D equals 0. And then on equation 3, it's negative C plus D equals 0. At this stage, it's effectively a null space. We can use a theorem in section 4.3 that tells us this is a subspace automatically. It's the set of solutions to a homogeneous system of equations. And if we like, we can turn it into a null space as well. So all I've done is reformatted the entire set. We haven't made any huge progress other than visualizing it with new notation. And the notation's kind of clunky with A, B, C, D. If that bothers you, one cool thing about set theory is in the set builder notation here, all variables, the way you decide to name them, are not the intrinsic thing about the set. You could just rename this x1, x2, x4 if you choose, and it's still the same exact set. Let's do that just for the sake of familiarity. This is x1, x2, x3, x4, such that, just rename this equation, x1 plus 2x2 plus 3x4 is 0. Then it'll be x3 minus x4 is 0. And then finally, negative x3 plus x4 is 0. So same exact set, just different variables. Sometimes these are literally called dummy variables because it doesn't matter what you call them. It's the relationships and how they're involved that really matters. But then at this stage, we can just say that this is null A, where A equals, pull from each one of these, the coefficients. We're essentially just changing from this system of equations into a matrix equation. The matrix would be 1, 0, 0, 0, or hang on, there's 3 equations there, 1, 0, 0. For column 2, we'll have 2, 0, 0. Column 3 goes 0, 1, negative 1. And column 4 is 3, negative 1, positive 1. So again, the reason we can do that is just because null A is a set of all vectors x, and there's the vector x, such that A times x equals 0. But all we've done here is taken the system of equations, wrote in the matrix, and so this just transfers directly into A times x equals 0. So the big punchline with this one is, if it's a homogeneous system of equations, and it is, it's effectively a null space. So we now need to find a basis for the null space, That means we're solving that system entirely, writing the solution down in parametric vector form, then as a spanning set. That will give us the basis automatically as a process. Any questions so far, folks? Just changing our point of view with the set to start it out. Okay, I think that's the hardest thing about this whole problem. The fact that a set H like this could be rewritten, scrambled to basically, it's like been disguised or it's been encrypted in a way to disguise from the fact we're just solving A times X equals 0. It's really nothing but a null space. So that skill from going here down to null A for the specific matrix A is a really important one. But solving AX equals 0, we can just immediately drop down to the augmented matrix. We're solving A augmented with that 0 vector. The right-hand side's highlighted above. So that's the matrix 1, 0, 0, 2, 0, 0, 0, 1, negative 1, 3, negative 1, 1. Here's the augmented part. Really fast row reduction on this one. Row 1 is 1, 2, 0, 3, 0. Row 2 is completely fine the way it is as well. 0, 0, 1, negative 1, 0. And then we'll just add row 2 to row 3. This wipes it out entirely. So row 3 is a zeroed row. In this form, we can solve for X directly. Variables go X1, X2, X3, and X4. So there's 2 pivot columns, columns 1 and 3. That means the free variables are X2, X3. But once you spot the free variables, one big hint and punchline with the next part is, once it comes back up, there it is. We basically know the dimension of H right at this spot. The number of free variables are going to tell us. We'll complete the problem because we're looking for a basis on part A as a kind of a review question to section 4.3, but that's an important concept in its own right. The moment you know the free variables, you know the dimension of the null space. So next step we would take is we would rewrite from this a system of equations where we solve for the basic variables in terms of the free ones. X1 equals negative 2x2 minus 3x4. X2 is a free variable, so we'll just write it as 1 times x2. 1 just to emphasize the constant we're going to pull out. X3 is going to be equal to, from this row here, positive x4. And finally, x4 is another free variable, so we'll just write it as 1 times x4. So for the free variables, we essentially did this to them. For the basic variables are solved in terms of those free variables. And now we can say that the null space of A, well, let's actually just solve AX equals 0, then go to the null space. AX equals a 0 vector implies the solution is X equals, take x2 times a particular constant vector. Same thing we did to build this set. We're just coming over here this time and pulling those coefficients. They go negative 2, 1, 0, 0. Plus x3. Same trick as before. Come over here to this column and pull those coefficients. Negative 3, 0, 1, 1. And we can say, comma, such that x2, x3 are in R, the parameters that are allowed to vary. But this is basically saying a spanning set. If we call these, say, V1, V2, what we've also concluded is that the null space of A is span of those two specific vectors, V1 and V2. So that's all this original set really was. This set of vectors with 4 entries is just the span of V1 and V2. Another really important concept, though, is we mentioned this a lot in section 4.3. We can tell visually, these are not multiples of each other, just from going row entry 2 to entry 2. If you go from a 1 to a 0, only way to make that happen is if you multiply this whole thing by 0, but there are other non-zero entries. So we have V1, V2 as linearly independent, but the larger, more important fact is the process of finding null A always, that's a strong word that does need an extra statement, always produces a linearly independent set. So that's linearly independent just by the nature of this is the process to get the null space. That's not completely true in every situation. So here is the catch-all, except when null A turns out to be the zero vector. The columns of A are linearly independent. That's the only one exception because that set is linearly dependent, having just the zero vector. So that's an important exception to think about. If it's not just the zero vector, if you found at least one free variable, the set you get down here is guaranteed to be linearly independent. But that means the problem is essentially over. We know the dimension of H just by the fact that there are two vectors in a set that spans and is also guaranteed to be linearly independent. This set without the word span is the basis. So let's finalize this problem here. We can say, therefore, a basis for null A is those two vectors, v1, v2. Let me put a box around this just as a way to convey this is the last statement that fully answered part A. There's just work kind of everywhere in comments. That's what we want to get, the basis. And now for the last problem, the dimension of the set H is the number of vectors in a basis. There's just two of them, so we can now say dimension is 2. That's a regrettable choice of color. Let's go with blue because this is not an accident or a coincidence. It's always the number of free variables that you found. If there are no free variables, that means A is invertible, and the null space contains just the zero vector, but that would mean no free variables is dimension 0 in that case. 2 free variables or 5 free variables tells you the dimension is 2 or 5, and so on. So these are two pretty big review problems altogether, section 4.3, going through again the steps of finding these bases. The new thing is just saying what the dimension is at the very end there. Well, any last questions at all, folks, going through either one of those questions? Okay, let's kind of recap on both of these questions. On the prior one, once we wrote down a matrix A and we visualized this kind of set as essentially being a column space, the number of pivot columns that we found gave us the dimension. And then from the other point of view, the number of non-pivot columns, the one that corresponds to the free variables, gave us the dimension of the null space. As another totally relatable fact as well, this is just an extra comment, we have a matrix A right here that's defined, the dimension of the column space of A in this particular problem is the number of basic variables, 2 of them in this problem. So if all we cared about is just dimension of either a column space or a null space, these problems are actually extremely fast. And that's what the next theorem is collecting all into one spot. I do want to make one additional change on this one. I had to fix the grammar. The word letter D was missing here. That was supposed to be and. I feel like this problem is a little bit more interesting if we change this to say 7. So sorry for the quick edit in the middle. I noticed that leaving this as a value of 4 works, but to really see the difference between the two when we say 2 free variables, that's just not a good number to work with. So let's make the quick edit on this one. Let it be a 5 by 7, just to make it more interesting. The theorem is the recap of what we were mentioning in those last two examples. The dimension of a null space is strictly the number of free variables, and the dimension of a column space is the number of pivot columns in A. In either case, you're talking about columns both times when it comes to null space and column space. So because of that relationship, when we are told that A is a size 5 by 7, the last theorem is about the number of columns specifically, not the number of rows. So that's kind of interesting. A theorem all about the columns and the number of rows does not matter whatsoever on this one. We're saying assume that this particular matrix has exactly two free variables. State the dimension of the null space and then the dimension of the column space. But these become really fast problems on the view of the last theorem. The null space A in dimension, we can write out dimension null A. This is equal to the number of free variables. So it would be equal to 2 exactly. And then that finalizes the problem. Then it tells us for the next part, the dimension of the column space, dimension column space of A, is the number of pivot columns in the matrix A. But there's 7 columns in total. And when it comes to the columns, they're either a pivot column or a non-pivot column. The variable is either a free variable or a basic variable. There's no middle ground, right, whatsoever. This is totally and 100% black and white. So if there are 2 free variables, there are 2 non-pivot columns. The rest of the columns here must be pivot columns, and that's the dimension of the column space of A. It has to be of dimension 5 now. The key fact about this is the total equals 7 is always equal to the number of columns. So spotting dimensions for either null space, column space of a matrix A is really, really rapid, especially if your matrix A is in, say, echelon form. That reveals the number of pivot positions. And this is another problem we could do just basically instantly. Kind of refreshing after the long problems, the last 2 problems that we did. Well, any questions at all, folks, with that theorem or last example? Okay, this one was kind of a more abstract question because all we know is A is a size 5 by 7 and something about the free variables. This one feels a little bit more concrete because we're looking at the matrix A right away. We want to do the same thing, come up with the dimension of the null space of A, dimension of the column space of A. And, in my opinion, I think if you're just given the matrix like this, the column space of A is the faster one to find. Because it's equal to the number of pivot columns, just find the pivots in the matrix A. Column 1 is a pivot column, as is this column, and this column. If it wasn't in echelon form, we would have to row reduce it to get into echelon form, but we don't need row reduced echelon form on this kind of problem. So we can conclude immediately that the dimension of the column space of the matrix A is 4, number of pivot columns in that particular matrix. And that doesn't leave pretty much any argument on what the dimension of the null space of A would be. So the number of free variables, and the number of free variables corresponds to the number of non-pivot columns. So we can say just immediately, dimension of the null space of that matrix A is, we have 1, 2, 3 free variables. And just as a quick check, this matrix is of size 4 by 1, 2, 3, 4, 5, 6, 7. 7 was just a coincidence. It happened on both. I should have changed that to a 6 maybe. If it's a 4 by 7, The two theorems that we used is all about the columns, so that's just a really quick check on this one. This equals 7, which is the number of columns. So just a fast check that we didn't miscount on anything, maybe misidentified a pivot column there. So dimensions are kind of nice if you're not being asked what the basis is, and you're just being asked in the problem, what is the dimension straight out? Definitely use these theorems. These are the kinds of theorems that could save you tons and tons of steps in, say, a final exam situation. If this problem comes back, you never needed to find the null space specifically of this matrix A, and it would have been a lot of work. This is what that work looks like essentially for a larger matrix. So definitely look into taking advantage of these tools when they come up, and particularly in the homework as well. Well, we have a couple more concepts that we want to take a look at before we close out the notes. Any questions at the moment? Okay, so just for additional practice, let's run through this one right here. This one is only asking for the dimension of the null space of A. And there's multiple ways to solve this one. You might notice that the dimension of the column space of A is 3. It has only 3 columns, and there's a kind of total that occurs every time. So if the dimension of the column space is 3 because 3 pivots, and there's 3 columns, you would put a 0 right here. Dimension is automatically 0, and that's a really great way to answer this one. So let's answer it in a slightly different way. Both solutions are totally fine. But one way you can look into this is you could say the determinant of A equals 1 times 5 times 11, because this matrix is upper triangular. We can just take the product of the main diagonal to compute the determinant. This is 55, which is non-zero, which implies A inverse exists. That means if you want to analyze this in a different way, you can now just drop into the invertible matrix theorem. We mentioned the invertible matrix theorem has grown a little in chapter 4. There's several new entries. So let's take a look at those new entries as a different alternative way of doing example 7. So 4.3 has the current updated invertible matrix theorem. Just trying to find a spot to park this. Let's see, where is the invertible matrix theorem that gets up? Here it is. So the invertible matrix theorem has new entries. Column space and the null space. Let's see here. There's some information about null space on part P, part N. These were the new entries in section 4.3. If your matrix A is invertible, the column space of A, it's a square matrix, so it fits the invertible matrix theorem. Column space of this matrix A would be equal to R3. Part P tells us, well, there's no free variables if you look into a null space. The null space of A contains only the 0 vector. Ax equals 0 contains only the trivial solution. So these are the two new entries that came from section 4.3. But now we have in section 4.5 two more new entries. The dimension of the column space of this one is 3. We know that because there's 3 pivot columns. The other new element is Q. The dimension of the null space of A is 0. So this happens every single time A inverse exists. We can really just immediately drop down to, by the invertible matrix theorem, by the IMT invertible matrix theorem, dimension of the null space of A equals 0 the moment you know A inverse happens to exist. So that's another kind of nice way to answer this question. We only answered it this way just as a way to look at the invertible matrix theorem one more time. It'll get a little bit bigger in chapter 5, and that's where it's going to make its maximum size. But any last questions, folks, on this last example or the new update to the theorem? Okay, so Next concepts we'll take a look into are finding out dimensions for these kind of spaces, the polynomial spaces. One thing we can say right away, because we know what a basis would be for Pn, is this comment or concept. Dimension of Pn is always just an n plus 1. And that's because it has a standard basis that goes from 1 t squared up to t power of n. The plus 1 is the constant term that you're going to get, the 1. Another really massive theorem right here that's just stated as a basic remark is one immediate consequence of dimension is the following. If you have two vector spaces that are finite dimensional, and you happen to know they have the same exact dimension n, this tells you automatically that those two vector spaces are isomorphic to each other. The only difference between V and W is how you notate the vectors, no other difference whatsoever. This takes us to another concept. If the dimension of Pn, all polynomials of degree n at most is n plus 1, and if the dimension of R n plus 1 is n, we know Rn plus 1 is n plus 1 because the standard order basis would be just the columns from an n plus 1 by n plus 1 identity matrix. But that tells us right away by this remark, Pn is isomorphic to Rn plus 1. They are literally the same vector spaces. Everything we did in chapter 1 with Rn plus 1, we could have done over in a different notation just by looking at polynomials. There's a little bit of a catch-all to that, though. We're saying that these two vector spaces are exactly the same. They're isomorphic. They have totally the same structure. But that's only when you view Pn through the operations of just vector addition, adding together polynomials, and just scalar multiplication, scaling polynomials. If you look at polynomials in full generality, there's other structures. You can multiply them, for example, but we're eliminating that operation if we're thinking of it as a vector space. So there is more structure here if you're going beyond vector space structure, but with the respective vector addition, scalar multiplication, these two are exactly the same. If they're isomorphic, that means there's a transformation that ties them together, a linear transformation, and that transformation is just the coordinate mapping. That's what we're using in section 4.4. We took problems like these, showed that they form a basis, just by applying the coordinate mapping. So let's do that one more time just for the sake of, again, another quick review problem. These are the first four so-called Hermite polynomials. There's three main interesting classifications of what's sometimes called special functions as polynomials. They're the Hermite polynomials, the Legendre polynomials, and the Laguerre polynomials. And there's other stuff like the Bessel function that sometimes functions considered to be special functions. They're used in all sorts of things, numerical analysis, signal processing, physics, things along the lines of, say, the strange kind of physics. I'm drawing a blank on what that is. We'll have to ask the specific physicists what interesting things they can do with this. But all we're doing in this particular problem is showing these polynomials form a basis for P3. One thing we can say right away, just to make sure we're on the right track, dimension P3 is 1 higher 4. So the fact that we have 4 vectors here is good. That means there's a potential for this to form a basis. But it also tells us that P3 is isomorphic to R4. And showing the work that it's a basis is far easier if we just translate the problem into R4. So that's what we'll do to start off this problem. Let's give these vectors names. P1, P2, P3, P4. Then let's work in a more convenient basis. Let me fix that subscript first. More convenient basis than what we have here is this one. Standard ordered basis for P3 goes 1, T, t squared, t cubed. That's where we're seeing the dimension is 4 because there's 4 vectors in this basis. Next, we can say, let A be defined by taking the coordinate mapping of P1 relative to the standard ordered basis of P3. Let's do the same to all the polynomials. So P1 through P4, take coordinates of every single one of them, and we're changing the problem to R4. This is the isomorphism, the one-to-one linear invertible transformation. Takes a bit of writing to say exactly what we're doing. So here's the last one. So all this notation is just telling us, what are we doing specifically? This is the section 4.4 problem. Every one of these brackets are telling us we're looking into the coordinate mapping, which means we're going to P1 and just taking the coordinates of this vector here relative to this basis. We are literally, like we did in the first week of class, just pulling coordinates. The way to write P1 as a linear combination of these 4 basis vectors is just take 1 times this vector. That means P1 of E goes 1, 0, 0, 0. Do it again for P2. This would have 2 times this t, so that means it goes 0, 2, 0, 0. For P3, we take -2 times the constant plus 4 times t squared. So -2, 0, 4, 0 on this one. Then -12t plus 8t cubed is just a linear combination, -12 here. So 0, -12. No t squares, so 0 there, plus 8t cubes. So that gives us the last constant vector. So this is how we dumped in those vectors. My formatting isn't perfect on that, so follow the arrows. But notice once we get here, we have, well, the dimension of the column space of A would be 4 because there's 4 pivot columns. Let's go with this route. There's lots of ways to finalize this question because of the vertical matrix theorem gives you the opportunity for lots of creativity. But I want to go with part O, the fact that the dimension of the column space of that matrix A is 4 because there's 4 pivot columns. So let's say this implies dimension of the column space of A equals 4. And so the columns of A forms a basis for R4. So let's go back to the vertical matrix theorem. We connected the dimension of the column space being 4 with the columns of that matrix A forming a basis for R4 itself. So that was connecting part O and part M in the vertical matrix theorem. We never even mentioned that A was invertible or that its determinant was non-zero. Those are the only 2 parts that we had to connect all together. So dimension is a pretty powerful tool, allows us to get to that conclusion as a shortcut. And then here's our overall conclusion. Through the fact that these spaces are isomorphic, and the fact that we use the coordinate mapping isomorphism, we can conclude P1, P2, P3, and P4 must also form a basis for P3. And that finally ends the whole question right here, right at that spot. So it didn't look like dimension would come into the problem because we certainly didn't use dimension in section 4.4, but we made it happen just to show how you can make that work if you decide to go the dimension route. But any solution that you found, any way of working through this invertible matrix theorem, if you took a determinant, for example, that would have been just as a valid way to see it. Well, any last questions at all, folks? Running through that example there. Okay, well, we've done a lot of work in chapters 1, 2, 3, and particularly in 4, where it got quite abstract. Chapter 5 is going to be applications to eigenvalues and eigenvectors. But you know, when you're doing chapter 5, you're basically looking into a null space again. To find the eigenvectors, you're looking into an eigenvector, a set of linearly independent eigenvector basis, vectors that form a basis for the null space. Essentially, you're just reusing all the tools and language that we've been building up so far with the new idea of what is an eigenvalue, what is an eigenvector. And even determinants makes a comeback in chapter 5. So chapter 5 is where we stop putting as many new concepts on a constant regular basis that are so abstract. We start just reusing the tools that we are developing in chapters 1, 2, 3, and 4. But we have a little bit more on the notes. We didn't quite get to this last bit, so this was if time permits. I didn't want to rush through the last problems because they were more important. If you're curious on showing P as an infinite dimensional vector space and CR is also an infinite dimensional one, I'll be happy to discuss that and fill out the notes. Just let me know. But we'll end the notes officially on this problem here. Well, have a great weekend, folks. Have a great afternoon. We'll be now in chapter 5 when we come back on Tuesday. Thanks, and here's this back for you. Okay, thank you. You bet.